Let's start with a new topic, that is variational autoencoder. So variational autoencoder are generative models explicitly designed to capture the underlying probability distribution of a given data set and generate novel samples. They utilize an architecture that comprises an encoder decoder structure. The encoder transforms into input data into latent form, and the decoder aims to reconstruct the original data based on this latent representation. VAE is able to generate new data samples resembling the training data. VAE's latent, or rather hidden, space is continuous. As such, the decoder can generate new data points that seamlessly interpolate among the training data points. VAEs find applications in various domains like density estimation and text generation. The architecture of a variational autoencoder, the VAE has two components. One is encoder connection and the decoder connection. An encoder network transforms the input data into a low-dimensional secret space, often called a secret code. The architecture is dependent on the technologies, and thus it is chosen based on the characteristics of the data. The encoder network produces essential parameters such as the mean and variance of a Gaussian distribution, necessary for sampling and generating the latent code. Similarly, the researchers construct the decoder network using various types of neural networks, and its objective is to reconstruct the original data from the provided latent code. A VAE comprises of an encoder network that maps input data to a latent code, and a decoder network that conducts the inverse operation by translating the latent code back to the reconstruction data. The training process enables VAE learned and optimized latent representation that captures the fundamental characteristics of the data, enabling precise reconstruction. Apart from the architectural aspects, researchers apply regularization to the latent code, making it a vital element of VAEs. This regularization prevents overfitting by encouraging a smooth distribution of the latent code rather than simply memorizing the training data. This regularization process not only aids in generating new data samples that interpolate smoothly between training data points but also contributes to the VAE's ability to generate novel data resembling the training data. Moreover, this regularization prevents the decoder network from perfectly reconstructing the input data, promoting the learning of a more general data representation that enhances the VAE's capacity of generating diverse data samples. In VAEs, researchers express the regularization by incorporating a pullback linear divergence term into loss function. The encoder network generates parameters, that is mean and log variance of a Gaussian distribution for sampling the latent code. The loss function of VAE includes the calculation of the KL divergence between the distribution of the learned latent variable and a prior distribution, normal distribution. Researchers include the KL divergence term to encourage the latent variable to possess distributions similar to the prior distribution. Here is a formula for the KL divergence. That is, I think it is easily understood by all those readers. KL Q within bracket Z by X and divided by P, probability of Z. E log Q to the Z oblique X minus log PZ. So in summary, the regularization incorporated in VAEs plays a crucial role in enhancing the model's capacity to generate fresh data samples while integrating mitigating the risk of overfitting the training data. Probabilistic framework and assumptions. The probabilistic framework of VAE can be outlined as follows. Latent variables. Now this is a crucial in enabling their representation within a model constructed using a simpler, typically exponential conditional distribution concerning the observed variable. It is characterized by a probability distribution with two variables, that is probability of x and z. While the variable x is visible in the data set under consideration, the variable z is not. The total probability distribution can be stated as probability of x and z, that equals to probability of x divided by z into probability of z. Observed variables. We have an observed variable x which is assumed to follow a likelihood distribution of p x oblique z. For example, a Bernoulli distribution. Likelihood distribution L, that is x and z, a function that depends on two variables. If we set this value of x, the likelihood function can be understood as a distribution representing the probability distribution of z for that particular spread x. However, if we set the value of z, the likelihood function should not be regarded as a distribution for x. In most cases, it does not adhere to the characteristics of a distribution, such as summing up to 1. Nevertheless, certain scenarios exist where the likelihood function can formally meet the distribution criteria and satisfy the requirement of summing to 1. The combined distribution of the latent and observable variables is as follows. That is, probability of x and z is equal to probability of x divided by z into probability of z. The joint probability distribution presents the probability distribution for multiple random variables. The main purpose of VAE is to understand the true posterior distribution of the latent variables, denoted as probability of z by x. A VAE accomplishes this by employing an encoder network to approximate the genuine posterior distribution with a learned approximation, that is q of probability q z by x. Posterior distribution. In Bayesian statistics, posterior probability refers to the adjusted or updated probability of an event happening in light of newly acquired information. Update the prior probability by applying Bayes' theorem to calculate the posterior probability. The VAE learns the model parameters by maximizing the evidence lower bound, that is ELBO. ELBO is equal to E and then the log P probability of x over z minus KL Q of zx divided by probability of z. So this is the formula for calculating the ELBO. So ELBO consists of two terms. The first term is the reconstruction term, which calculates the ability of the VAE to recover the input data correctly, and the second term, the KL variance, defines the difference between the estimated posterior distribution and prior distribution. By employing a probabilistic framework, VAE models generate the data assuming that the input data from the latent space is on a specific probability distribution. The objective is to learn the true posterior distribution by maximizing the likelihood of the input data. Thank you.